Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello, and thank you for choosing IT Pro TV, helping you learn everywhere you go. I'm Zach Memes, your host as we continue on with CompTIA Net Plus. Network Traffic Properties is the title of this episode, and Wes Bryant is here once again to help us out because he likes us. Wes, it's good to have you here. Thanks for joining.
Hey, Zach, thanks for having me back. That's right. You know, you guys are okay. You're all right with me. I don't care what Zach says about you. No, just kidding. That's right. We are back to talk about, you know, the different characteristics, right? The properties, if you will, of our network communications. Because believe it or not, really all we've been talking about is, you know, the source and destination, right? The endpoints of communications. And we've been talking about the redistribution points, right? Whether that be your connectivity devices or a repeater, right? But we have to look a little bit more in depth on some of these characteristics, right? Some of the properties, because in certain scenarios, your computers might communicate one way. Another given scenario, your computers might communicate completely different. And then in other ways, they all will differ from all the other ones that we're talking about as we go into this episode. So it's going to be important for you guys out there to understand some of the characteristics or properties that we're going to take care of here in this episode.
So, Wes, it sounds like you're talking about there's more than one communication type. So can you tell us a little bit more about that?
Most definitely. You know, when it comes to communications, we largely it's broken down into three of the most common. There's a fourth one here that isn't on the list. So, Zach, I'm going to throw you a curveball and kind of steer off the beaten path when we get to that fourth one, because even though it's not called out on the exam, I want you to be prepared for it, because we know here at IT Pro TV that many of you that are going to sit the Network Plus exam might go on to other certifications. So it's not always just about what is on the exam, but try to give you some additional information even if they don't call it out. So the very first one I want to call out is, and I got a little diagram here, and this communication type is what's known as a unicast. And when we look at unicast is a one-to-one communication, all right? That is when, that's really what it boils down to when we say we got a source of the communication and we got a single destination, right? Source and destination, that's a unicast. So, for instance, if I'm going to communicate, let's say Zach and my computer, I'm going to send him some information, right? Or maybe I'm going to connect to his computer over like a share, if you will, like a shared resource that's on his computer. It's a straight one-to-one communication, right? Or if I do something like maybe I ping Zach's computer from my computer just to see if test reachability, right? And I get replies back. Well, those are one-to-one, right? One-to-one communication is what we know as a unicast. Now, I do want you to understand that in a unicast, no other computer, none of these other computers actually receives any signal. And that's important, right? Not only to know that it's a one-to-one communication, but also to know that these other computers aren't going to receive that communication. Now we have another type of communication, and that's what's known as a broadcast. And that's really, Zach, that's the polar opposite of a unicast. When we say unicast being one-to-one, a broadcast communication is like going to the food court in the mall, standing up on the table and yelling out, and everybody hears you, right? That's a broadcast, and hence why they call it a broadcast, right? It's a one to everybody within earshot of that broadcast communication, and we'll come back to that a little bit later. So notice that the source of the communication here sends a broadcast into the connectivity device, and then that connectivity device turns around and literally sends it out all of its ports. All right, so that is important to remember, that broadcast communication is one-to-all. So we have unicast, a one-to-one communication, and we have a broadcast being the opposite of that, being a one-to-everybody, one-to-all communication. Now we've got another one. This is the third most common type of communication that you have on your networks. And the third most common type of communication is what is known as a multicast communication. Now, a multicast communication is a little bit more efficient than a broadcast. Broadcast communications, if you have too many of them on your networks, they can negatively impact the performance of your network, right? If you think about it, if I only have to talk to Zach, there's no reason for me to stand on the table here and yell out to where everybody else in the studios can hear me, right? There's a lot of wasted information, or wasted hot air in my case, but wasted communications if we bring it back over to the network, right? I only needed to talk to Zach, right? Well, what if I needed to talk to, let's say, Zach here in Studio 2 here, maybe Mr. Gordon over there in Studio 4 right now, and maybe Miss Cherokee over in Studio 1, but I didn't need to talk to anybody else. Well, that's where the multicast comes in. Now, I want you to understand that you'll hear it commonly said a one-to-many, right? We have the unicast, one-to-one. We have the broadcast, one to everybody. But what is one-to-many? As I've been teaching this over almost a decade now to a lot of our members now, but the students that I used to in the past, I would say, I want you to change that many, all right? Change it a little bit. That's absolutely right, and that's what you're going to hear the majority of a lot of documentation out there. But I want you to understand that it's actually a select few, right? That many is chosen. It's not just some random arbitrary number. It's a group. It's called a multicast group. And I want you to think about it as like back in the 90s, I remember, and even the 80s, I remember, when we were a little bit younger, we would get somebody, one of the kids' moms that had like a pay-per-view event, right? And we'd all do chores or something, and we'd all get our money together and we'd put it in a collection pot and we'd give it to one of the moms within the neighborhood. And she would order the prize fight. We'd watch Mike Tyson, right? We'd watch Evander Holyfield, right? We would watch the prize fight. Well, think about the pay-per-view and how it's going. You can have everybody in that neighborhood has the same cable company. And most likely in those days they did have the same cable company. But who is going to receive that pay-per-view event? Now, I'm not talking about you hackers out there. I'm talking about legally. Who is going to receive that communication? Only the people that were part of the pay-per-view event, right? Well, that's the same thing with a multicast. Let's go ahead and tie some of these other concepts together that we've talked about in the past as well. All right, I want you to think of IGMP. That's the Internet Group Management Protocol. The Internet Group Management Protocol, what it's responsible for is it's the protocol that we use to send multicast communication. So your connectivity devices, when they need to send a multicast communication, what do? They use IGMP. And in fact, I've got a Windows 10 machine here. I can kind of show you how our computers are, since this is under the domain, apparently I don't remember how to type my password. Since this is under the domain of routing and switching, it is kind of good to kind of see this in action. So let's go ahead, and what we'll do is I'll launch up my command prompt here. Let me go ahead and clear the screen here and give us a little more real estate. And in our network troubleshooting tools, we talk about a command, and go check those out if you will, because we're not really going to dive too in depth on what this does, but we talked about a route command, being able to view the routing table. And if I do a route space print -4, I can view the IPv4 routing table here. And the reason my computer knows where to send multicast communications is because it's aware of the multicast networks. Tying another concept together, remember we're going to start tying the pieces together of everything we've been learning here in Net Plus. I want you to think of that class D range, right? In the classful system we have A, B, C, D, and E. Don't worry about E. E's research, experimental. It was never given over to anybody in the public. It was used for ARPA, the military, if you will, and universities for research. But D range is the multicast range, and that's never allocated to any one computer, right? If I'm an ISP, Zach doesn't come to me and say, hey, I need internet access, and then I give him a multicast address, right? All of your computers use these addresses, right? When they need to send a communication, they say, hey, I'm going to start a multicast group, and they send it to the multicast address. The listening connectivity device says, oh, okay, I'll make a multicast advertisement that says, hey, there's a multicast group over here. If you want to join it, communicate with me. And then when my computer needs to send multicast communications, it sends it again in that one-to-many fashion to everybody that is in the group. That's the multicast, all right? So, recap. We got unicast, one-to-one. We've got broadcast, one to everybody, right? Getting up on the, the table and yelling out at the top of your lungs. And then we have the multicast, which is a one to a select few, one to a group. Now, there's a fourth one here, and I don't have a diagram for this one, and honestly, it really isn't even in the exam objectives, but there's another one that's on the scene, too, that I'm going to go ahead and mention so that those of you that are going to use Net Plus to leap off into higher level certifications will be aware of, and it won't catch you off guard. And that's called an Anycast. Now, an Anycast is an interesting thing because an Anycast isn't a one-to-one, isn't a one-to-many, isn't a one-to-all. It's what's known as a one to the best. One to the best choice, all right? I'll give you a classic example of where you see something like an Anycast, all right? In our DNS episodes, we talked about the root, the hierarchical system, and when my DNS server doesn't have the answer, what does it do? It needs to communicate with the root hint server, right? Well, where are those root hint servers? Well, there's actually 13 IP addresses for those root hint servers, all right? And I think it's alphabet letters A through M. But 13 IP addresses doesn't mean there's 13 root hint servers. There's actually hundreds of root hint servers all around the world. All right. Well, when I need to contact, my DNS server needs to contact a root hint server, the router's going to look at it and say, okay, well, what's the best choice? You've got a lot of root hint servers out there. So it does an Anycast, and it sends that request out to the closest or the best choice. So the Anycast is one not on the list and out here off to the side, but it is one that you should be aware of. It is the one to best. Now, there's something else that we have to understand too, and that is the fact that, you know, we talk about two different media access methods, I'm sorry, connectivity network types, if you will. One is what is known as contention-based media access. The other one's known as deterministic media access, all right? Ethernet is what we use today on our LAN communications. It is the most common local area network. It dominates the market, right? Well, why is that? Well, it's a cheaper implementation than some of the earlier, if we take a trip in our DeLorean and go back to the future, back into the 80s, where there were other competing technologies for LAN-based communications, but they kind of fell by the wayside. And some of these were deterministic media access, all right? And what is the difference, okay? Well, contention-based media access does this. It says, every one of the devices on that network are going to contend, right? Could have been a contender, right? They're going to contend. We're going to come back to prize fight somehow here, Zach.
Hey, you're like Rocky.
That's right. So what they do is they all are in a competition to send their data. They send their data, they send their data, they send their data, and they hope it gets to the endpoint. All right. Now, there's a benefit to that and there's a drawback. All right. The benefit is, because the computers are the ones that are communicating back and forth and they're the ones that are contending, it brings the price of your connectivity devices, since they don't have to worry about that contention, down. So the cost is lower, hence one of the reasons Ethernet won out. The other thing to keep in mind too is that deterministic media access, all right, now there's a benefit to it, but then there's also a drawback as well. See, deterministic media access is like this, me saying, Zach, do you have information that you need to send? No? Okay. Somebody else. Do you have information that you need to send? Oh, you do? Okay. Well, you can send your information now. And as we go around this circle, we're going to let everybody know that you've got information that's on the wire. And Zach, myself, and everybody else that's connected to that network, you got to be quiet and wait. Right? That's deterministic media access. Now, there's a benefit to it, right? Everybody's guaranteed access to the wire. And I say wire figuratively as the network, right? All of your devices are guaranteed that they will have access to the wire, all right? Now, there's a drawback. Well, when somebody's using the wire, everybody else has to shut up. Everybody else has to keep quiet, right? Can't communicate. The other thing is, do you notice how I said, hey, Zach, do you have information to send? Now, Zach, I didn't even give him time to respond here, honestly, but Zach didn't say anything, right? That's a method called polling. I have to ask, Zach, do you have information to send? And if Zach doesn't have any information to send, well, there's a chance I wasted a little bit of time. Not that I wasted time on Zach, it's just the fact that I wasted time in the network asking a node, or Zach in this case, did you have information to send? And you didn't. So now we go to the next person. Oh, you didn't? Next person. Oh, you didn't? So there's a chance that we could go around a few of these computers and in the polling process and nobody has to communicate. So with contention-based media access, you're just, again, in a competition. And again, deterministic media access means more logic in the connectivity devices, raises the price point too. Then also, once Ethernet got beyond 100 megs and then into a gig at the lower prices, that's one of the reasons that just made it really, really attractive to a lot of businesses. Now, with contention-based media access, that leads us into the next concept that we have to watch it. In the earlier days of communications across Ethernet-based networks, we were in a bus-based network, right? Remember the bus topology. So we're kind of tying a lot of pieces together here in the traffic properties, right? We had those bus-based networks, and what was it? Remember, it was a single coaxial, almost like a network backbone, and then you would just attach nodes to that backbone cable. One computer would send information, and everybody else would hear it broadcast, right? But only the person, or the node that it was intended to, the recipient, would actually process the information. All right? And I want you to think of it this way. If everybody is contending and sending their information out at one time, then there's a potential for what's known as collisions. All right? That group of nodes is in what is known as a collision domain. Now, I want you to also understand that in the topology section, we also talked about a logical bus. We said you can have a physical star, which means, and in fact, let's go back to my multicast drawing right here just for a second here. Notice that, let's just say that this is a switch in the middle, right? I know it's a diagram for a router, but let's say it's or not a switch, I'm sorry, but let's say that it's a hub in the middle. Well, I want you to understand, remember what we said about a hub? Even though this is a star topology, right, physically, when one communication goes into, and I'd probably be better even to go over to our broadcast, because this is actually, know that this is a physical star topology, but because of the hub, the way the hub works, it receives communication and just broadcasts it out all our ports. That means every communication that goes into the hub is going to be broadcast. It means there's a potential for an electrical collision, especially when you have shared media. That is what's known as a collision domain. All right, and what it means is that if PC1 sends information into this hub, it's going to broadcast it out all other ports. That means there's a potential for two of these PCs, if not all of these PCs, to try to send information into the hub at the same time, and we get an electrical collision. That's what's known as a collision domain. And you have to understand that anytime you put a hub in your networks, you increase the contention because it's all broadcast communications, and you actually degrade the performance of your network.
And Wes, can I bring it back to a certain point? A little bit earlier, you mentioned about being within earshot of a broadcast domain. Now, what exactly did you mean by that? Yeah,
well, when I said, being within the earshot of a broadcast communication, that is what is known as a broadcast domain, right? If I said that if you can hear that broadcast communication, well, what do I mean by that? Well, every communication, if we look at our hub, right, every communication is essentially a broadcast communication, just the way it's electrically hardwired. It has no logic. It doesn't look at addresses at all. But at layer 2, we have switches, right? And switches inspect MAC addresses. Well, believe it or not, there is a MAC address for a broadcast communication, right? In our IP addressing, we talk about having a broadcast address for the network, right? And that's the IP address that a computer sends a broadcast communication when that computer over IP wants every node within that subnet to hear what's going on. Well, that's also layer 2 that happens as well. Understand at layer 2, in fact, I can kind of show you this, there's actually a broadcast MAC address. And if we use another command that we've used in our network troubleshooting tools, ARP, we do an ARP-A, we can actually see that right here, that there, oh, and you know what? I do not see it. Oh, yes, I do. I see it right here. Sorry about that. Here is the IP address. That's the layer 3 broadcast address. But remember, we're talking about the OSI model. We still have the data link layer. All Fs is a broadcast communication there at the data link layer, and that's what switches respond to. So when this switch receives a broadcast communication, so let's follow this train of thought here down the wire, quite literally. So PC1 sends a communication into the hub that is addressed to all Fs, that broadcast address. Remember, the hub, it's dumb. It doesn't look at that address. It doesn't care, doesn't know any logic at all. It receives the information and it broadcasts it to everybody that's connected to it, including the switch. Notice how the switch is also connected to the hub. Now, the switch is going to, this is where we start to get into the logic, right? That's what differentiates a hub from a switch. A switch is looking at the MAC address and it's saying, oh, I see the destination. The destination is all Fs. So you want this to be a broadcast communication. So what does the switch do? The switch broadcasts that communication out all of its ports. And when it does that, every device that is connected to that switch will receive and is within the earshot of that broadcast communication. Does that make sense now?
Yes.
So that means if this, and again, let's kind of follow this down the wire so we know what's going on. PC1 sends a broadcast all Fs as the destination MAC address in that Ethernet frame. It goes into the hub, hub's blind to it. Hub doesn't look at addresses. It just looks at raw bits, and it's like a repeater. It just broadcasts it out all other ports, including sending it up to the switch, because the switch was connected to the hub. But then the switch says, oh, that is a broadcast communication, and it floods that out all of its ports, including out to this hub and then back out to these 3 computers here. All right, now, one of the reasons we don't use hubs anymore in our networks, or you shouldn't be using hubs, is because you increase the competition. All right, if a hub is just like a logical bus topology, which if one computer communicates, everybody hears it within the network, well, then the more computers I hit to that hub, the more competition we have, the more hubs and more computers. You're just creating one big broadcast storm. The one great thing about switches today is that switches isolate contention domains, right? Because essentially what we've done is we've removed the hub, we have plugged each device, if you will, into its own port on the switch. And if you check out the network devices that we've talked about, the hub can forward between each ports based on its destination MAC address. So essentially what's happening is each computer is now on its own collision domain, but I want you to know that this would still be a single broadcast domain, right? According to the switch, if it sees an all F destination MAC address, it's going to send it to every computer that's connected to the switch, which is the larger portion, if you will. That's the broadcast domain. All right, so know a little bit of the difference between the broadcast domain and the collision domain. When you have a shared media where there's competition for that shared media, you have a collision domain. Because we don't use bus-based topologies anymore, we don't see too many of these, like a lot of competition going on, but you still have broadcast communications using broadcast domains. You put a hub into your network, and now you've essentially created a broadcast or a collision domain, if you will. So definitely understand that, because how it affects your communications, how it affects the performance of your network really matters. The more hubs, the worse your network's going to be, because again, what you're doing is you're increasing how much extra communications are going on your network. And what I mean by that, if we go back to our diagram here, what if PC1 only really needs to talk to, let's say PC1, 2, and 3, right? PC1 only needs to talk to PC3, and in the MAC address is the destination MAC address for PC3. Well, it doesn't matter the hub. It doesn't understand that. It just receives the signal and it broadcasts it out all the ports. So that means PC2 is going to receive the signal as well. It's not going to process it. So again, you can see there's wasted time, wasted communications on your networks. That's why we got to worry about broadcast communications. And that's why I said earlier on when we first started this episode that you have to be careful. You have to know what type of communications are going on, because in certain scenarios, you will communicate differently, right? If I'm sending a one-to-one communication between source and destination, I'm sending a unicast message. There are times where we need to use IGMP, Internet Group Message or Management Protocol, and what we end up doing is essentially the node is saying, hey, I've got a multicast group, sends the communication to the multicast address, makes the connectivity device aware that there's a multicast group, and then that connectivity device turns around and advertises the fact that, hey, there's a multicast group out here, and if you want to join it, just talk to me, and I can get you that information, right? And then, obviously, the broadcast is one to everybody, and we really don't want, there's times when we have to, right? It's not something that we can get around, right? You're not going to eliminate broadcast communications until you go to IPv6 and we're all IPv6. See, IPv6 does away with broadcast. There's multicast, unicast, and anycast. That's all. All right? Because we still have in IPv4, we have technologies that rely on a multicast communication. Like, let me tell you specifically, we've talked in other episodes about ARP, the Address Resolution Protocol, right? And here's our ARP table here on my Windows 10 machine. Remember what's going on with ARP. Remember that it doesn't understand the IP address. So if I run ipconfig, right, and this is my IP address for this Windows 10 machine, if that router is delivering to, the routers are passing information across themselves and it gets to the destination network where my computer 10.10.10.10 resides, IP's dumb. It does not understand a MAC address. So what does it do? It hands it over to the Address Resolution Protocol, the IP address, and says, man, I need your help. Help me out here. And then ARP, Address Resolution Protocol, turns around and sends a broadcast, stands up on the table in the food court and says, who has 10.10.10.10? and then my computer's listening. Now, all the other computers heard it too because it was a broadcast communication, but they don't respond because that's not their IP address. And my computer sends an ARP response message back and says, hey, tell old lazy IP out there that you can find 10.10.10.10, and then what it does is it turns around and it gives, well, my MAC address. If I rerun that IP config all, if I can spell, I cannot spell all today, Zach. How do you spell all? I can do it. There we go. Then it turns around and says, hey, you know, you can find this IP address at this MAC address. I'll get it right here again eventually. At this MAC address. We'll get this right again. Hopefully you guys took your Dramamine out there, got your seasickness going. So that's what ARP does. It says, hey, tell the router in this case that 10.10.10.10 is at this MAC address, and then IP can finish the delivery to the local network. So again, there are reasons you have to know the characteristics, the properties, right? Characteristics, properties, I keep saying they're interchangeable. It's not technical jargon that's going to get you on the exam. Know those, but I will tell you that we've got a little bit more to go, and it doesn't look like we have enough time in this episode.
But you're doing a wonderful job, Wes. Network Traffic Properties Part 1. There will be a Part 2. Make sure you see both parts and see everything inside of CompTIA Net Plus that Wes has put together for you. And when you're in that course library, hundreds of other videos, all designed to help you go further. Thank you for watching. And you know what? IT Pro TV is binge-worthy. I'm Zach Memis.
And I'm Wes Bryant.
And we will see you soon.
Thank you for watching IT Pro TV.